Hi everyone, my name is Mei Mei. I'm a second-year PhD student in Department of Chemistry, and my research topic is on developing conductive and stable supports for iridium oxide water oxidation catalyst. So I just got back from a holiday in China where I was developing new skill, snowboarding. It was really fun, but a little bit hurt. And I noticed that they had to make a really huge amount of fake snow every day at the ski slope. And I spoke with the manager there, and he said the cost of maintaining a ski resort is very high, especially for these years. We are undergoing warm winters. So that's the evidence of global warming, and it's closely related to the CO2 content in the atmosphere. In order to prevent these tragedies like glaciers melting, forest fire, and drought from happening, we need to find sustainable replacement of fossil fuels. Well, renewable energy is a great option. However, they are quite intermittent, like solar or wind. And the availability and efficiency of renewable energies can vary greatly depending on the geographical locations. So storing renewable energy remains a significant challenge. Proton exchange membrane water electrolysers is considered as one of the most promising technologies to be coupled with intermittent renewable energy sources. So what is PEM electrolysers? So it has two electrode, anode and cathode, where oxygen evolution and hydrogen evolution reaction are happening to split water into oxygen and hydrogen. And there is a solid solid polymer membrane to separate these two electrode. And because of this solid membrane, it enables the operation at very high current densities. I'm sorry.
Electrolytic osmosis. So you're basically using the principle of osmosis via electrolysis, right?
Yeah,
that's what
maybe.
Is it? I'm just asking them. This is actually a genuine question.
What is that?
Osmosis, the diffusion of water, right?
Oh yeah. So it enables the proton Yeah. You're right. Good. And so this solid polymer membrane, it enables very high operation at high current density and the fast startup and shutdown dynamics compared with alkaline water electrolysers in industry. And it also has less hydrogen and oxygen crossover issue, which makes it safer to be decentralized. The main factor that hinders the mass implementation of PEM electrolysers is that it uses precious metals like iridium and platinum as catalyst. And
what, sorry? What?
Iridium and platinum, precious metals as catalyst. Platinum.
Oh, platinum.
Yeah, platinum.
You actually need platinum?
Yes. So we need iridium and platinum as the catalyst for hydrogen evolution and oxygen evolution reactions. Yeah, they are very expensive. Exactly. And platinum has been reduced effectively to 0.025 milligram per centimeter square because of carbon. So they use carbon as a catalyst support. That's why platinum can be reduced. However, there's no, carbon is not stable under water oxidation conditions. It will be corrode quite a lot. And it's really challenging to find catalyst support for iridium to catalyze water oxidation. So the real problem is at the anode part, iridium. So recent analysis showed if we want to meet global energy demand on a terawatt scale, and considering the annual production of iridium, we need to reduce iridium loading by a factor of 40 to 50. So from 2 milligram per centimeter squared to 0.05. Well, as mentioned before, it's challenging to find stable and conductive support for iridium because most of the materials will go through oxidation, subsequent passivation, and dissolution under the OER conditions. And iridium, it has achieved a good balance between activity stability and conductivity. That's why it remains the state-of-the-art OER catalyst and seems to be irreplaceable. Titanium dioxide is very stable, but it's roughly 20 orders of magnitude less conductive than titanium metal when being fully oxidized. But iridium is still very conductive when oxidized. And the porous transport layer in PEM electrolysers is made of titanium mesh. So if you accidentally form 100 nanometers of titanium dioxide, and also considering the very high current density in PEM electrolyzer, you will need extra 200 volts to break through this oxide layer. The thermodynamic water splitting is just 1.23. So yeah, there's no way for titanium dioxide to be a good electrocatalyst. Commercially available iridium oxide, titanium oxide catalyst still requires 70% of iridium loading to sustain the activity and the conductivity of the catalyst layer. And when we put them into PEM electrolyzer, the ohmic drop is taking up a significant part of the overall cell voltage loss. Another very popular oxide to be used as a catalyst support is doped tin oxide. So dopants like niobium, tantalum, and antimony have been used to improve the conductivity of tin. So it's possible to further reduce iridium loading to around 10%. However, these doped tin oxides are still less conductive than iridium oxide because the conductivity has been improved a lot when mixed with iridium oxide, and there's no clear trend in the activity of the water oxidation. Sharofko and his co-workers also reported similar results. There's no clear trend, and what's worse, the dopants in tin oxide seem to be leaching out during the reaction and even accelerated the degradation of tin. So as mentioned earlier, iridium oxide is still very conductive, and with these powdery samples, it's hard to exclude the conductivity contribution from iridium oxide. So in my project, I'm looking at the thin film. I fabricated OER support into thin films for iridium to sit on, so we can get well-defined surface area of the support, and it's easier to measure the conductivity, as well as we can preclude the conductivity contribution from iridium oxide. And so we've got a really expensive iridium oxide sputter target to sputter iridium on top of this support. So it has an even a distribution on the support. After a few months optimization, we can now get highly reproducible and crystalline iridium oxide at room temperature. So that's
How did you do that?
Sputter deposition.
What is it?
Yeah. So it use very high voltage and use Mach neutral to accelerate that high voltage to break down the carrier gas like argon or oxygen and strike plasma. So it,
So you run a high voltage
yes.
into,
So between the target to the substrate, so there's very high voltage, so I can strike plasma by this voltage. Yeah.
so you create plasma,
Yes, yes, create plasma.
and when it cools, it leaves that.
What?
When it cools down,
Yeah.
because you're gonna heat it up, does it
Oh,
leave that?
well,
It leaves-
I used, it's not really heat. When I'm saying at room temperature, I didn't put extra heat on the substrate. Yeah,
you just
so
run an electric current through it.
yeah, I just run like voltage and plasma on that. So after deposition, we can just take out the substrate from the chamber, and it's still cool. Yeah, so it's impressive because we don't need to.
That's efficient.
Yeah, it's efficient, and we don't have to oxidize. We can avoid oxidizing the support.
Spend less money on thermal energy. Thermal energy costs a lot of money.
Yeah, exactly. Yeah, exactly. Yeah. Cool. Yeah. So the main purpose of this project is to reduce iridium loading. So the question is that, which means that we need to make the best use of each active site of iridium. But the question is that, can each active site be active enough so we can reduce the number, right? So we sputtered crystalline iridium oxide of 1 nanometer thickness and 50 nanometer on top of a gold support. Gold is a most commonly used backing electrode to study water oxidation. And surprisingly,
Why?
Yeah.
Why?
Because gold is quite stable under water oxidation. Well, it's relatively stable, and it's still conductive.
Wouldn't silver be more effective? Silver's
No,
effective.
no, silver. So, in the water oxidation condition is really harsh. So we have acidic electrolyte and the oxidative potential. Silver will just dissolve
Oh,
straight away. Yeah, it's too light, so it oxidize and dissolve. But gold it has really loose. It just doesn't bind with oxygen, or it bind very loosely.
Low oxygen.
Yeah, exactly. Yeah. So gold is, well,
It's
for
heavier.
now it's
Easy, spacious.
yeah, it's heavier. So that's why we use gold, but gold is not a good option. We'll get there.
Yeah, no, it's like to know, you know.
Yeah.
That's just us. So you can be comfortable.
Yeah. It's cool. Thank you.
You're welcome.
Yeah, so from this 1 nanometer iridium oxide outperformed 50 nanometers of iridium oxide. But surprisingly, we can usually estimate the electrochemically active sites by the non-Faradic capacitance. So 50 nanometers of iridium oxide has a larger capacitance, but we don't know why it behaves worse than a thinner one. Maybe the conductivity effect is more pronounced at a thicker sample, because iridium oxide is less conductive than gold, or there is some size effect because it's like really small nanoparticles. But still, yeah, the resistivity of iridium oxide.
Yeah.
Maybe that could be, but we haven't.
Probably is. Do you know what I mean? Because if you look at it, you probably look at it from a chemist's perspective. From a physicist's perspective, increase the thickness, increases the resistivity. Therefore, the resistance will be greater. Therefore, more energy is needed to supply.
Yeah, exactly. But what we don't understand is that why it has more active sites. So from capacitance, we can know it has more active sites, but there's, we're still looking for measurements, like for techniques to so we can measure the through plane
No, I understand.
conductivity.
I understand.
Yeah, I agree with you.
The only thing I don't really fully get is the sputter thing. Like you run an electric current and then it creates all of that from basically nothing. And how did you generate the plasma to do that?
Yeah, I think so. We have carrier gas like argon. argon has, why we use argon is that it has the highest ionization energy. So it's like a bombardment. So it's like collect with the target and to strike plasma, like to strike single atoms. Like it sputter single atoms out of the target. So
I get you. I think I understand what you're saying. They can basically carry an electric charge,
yeah,
without the threat of an explosion. Is that what you're saying?
Yeah.
It's a noble gas. It's inert. So
Yeah,
it has a low reactivity.
Yeah.
High electric conductivity because the outer shell is full. Right?
Yeah.
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 Just checking, innit?
Yeah, I agree with you.
Understand this properly. Activation. Can I have the lecture slides when you're done?
Yeah, of course.
Send it to me.
Yeah. I can also show you what our sputtering look like.
Really?
Yeah. So
Well,
it's basically like this.
After this?
Yeah. No, it's at West City, but maybe some other time. Yeah, so that's the plasma, how it looks like. That's argon plasma is pink. It's pretty. Yeah, and that's the sputter, that's a target. And this is the substrate. Yes, of course. Definitely. Yeah, it's chemistry lab. It's not allowed to touch anything without gloves. Gloves, yeah.
You take them off when you go home.
No.
So,
Yeah.
Is this all you? Like, did you draft all these graphs?
Yeah.
Really?
Yeah, that's my experiment. So cool.
How old are you?
Yeah. 25?
No, it's back to
Yeah, it's my second year PhD, so still have lots of time to do to optimize the stuff.
We call it grafting.
Yeah.
We're working.
Yeah.
Yeah,
It's nice.
What's the substrate made of again?
Sorry?
The substrate, what's it made of?
Substrate.
Yeah, what's it made of?
You mean the substrate I sputter samples on?
So it says gold, the iridium
Oh, this substrate
Yeah,
is glossy carbon.
Carbon.
Yeah.
Just normal carbon.
Glossy carbon. So it's very hard. It's hard carbon.
What? So it's clear? Is it see-through?
I think it's a combination of C2 and C2 and C3.
C2.
Yeah, you mean C2 and C3.
C3.
Yeah, so C3 is not very conductive. There must be some.
Know what it was.
Yeah, it's hard carbon. I think they annealed this carbon at really high temperature, but in argon or some inert gas to make them really relatively corrosion resistant.
Really?
Yeah.
You make this in the lab?
No. We got.
You buy it from,
yeah, buy from.
Industry.
Yeah. And then I sputter 100 nanometers of gold and then iridium oxide. So gold can prevent the corrosion of the carbon. Yeah. Yes, so we are still investigating why 1 nanometer of iridium oxide.
I genuinely think it's the resistivity.
Yeah, but we need evidence. We need to measure it. We just not we can't see. We think.
Mendeleev.
It's not scientist.
Mendeleev didn't need evidence, yet we still use everything.
Yeah, it's tricky to measure the through plane. So we have to measure conductivity this way.
Which way does the current flow? Up?
Yeah, like this way.
So it is the resistivity as you go up.
Yeah, but
I mean,
yeah, we need techniques to measure.
it's not like a wire. With a wire, if you increase the cross-sectional area, then obviously the current.
Yeah, I see. Yeah, I know that. It's like the equation. Yeah.
But it's different if you're flowing electricity going up. It's much more different because it's not like you're increasing the size of where it's flowing through. Increasing the diameter means that you're adding more electrons. You're making more electrons along the surface. But in this case, you're just creating a greater distance for the electrons to travel. That's why I generally think it's the resistivity. Because resistivity is only meters larger than distance.
Yeah, but I don't think the resistivity is that much because it's nanometers.
Yeah, but you're basically saying Okay, so imagine you're keeping the electromagnetic force, voltage constant, right? It's about 240 volts, right? We're using mains electricity. Right? Exactly, so it's about 240 volts. We're slapping 240 volts, through so what if resistance is equal to resistivity divided by the distance, Therefore, if you increase resistivity, you increase resistance, The voltage is constant, therefore I is equal to V over R. If you increase the resistance, so the current is going to be lower. Simple physics.
Yeah, but that's catalysis.
Huh?
It's catalysis.
Yeah, of course. Well,
it's not always resistance.
It's still, but still electricity. Electricity is governed by Kirchhoff's laws. It's still the same thing. I genuinely think it's the resistivity. But we should. Why don't we design an experiment and measure it?
Yeah, I was developing that.
Really?
Yeah.
I hope you.
Oh, really?
Yeah, genuinely, I hope.
Okay. Yeah, we can have a discussion later. Yeah, so if the good news is that we can it's totally feasible to reduce iridium loading by a factor of 50 as long as we have enough gold as a catalyst support. But we can't use gold in PEM electrolyzers because it's still very expensive and rare. So
gold is rare.
It's expensive.
Oh,
and it's not that much.
How much is it per kilo?
I'm not sure.
Almost $2,000.
Yeah, I have a like diagram here, so it's like annual production. It's not very rare, but it's like 3 compared with yeah. We need to keep the cost as low as possible.
What is the budget? What's your budget?
I don't know. I think that's economics. That's not my thing.
But it's still numbers. As in, like, how much do they give you to spend? Like, how much do they give you to spend? Well, okay, let me ask you a simple question. How much does all of this cost you? Not how much they give you. How much does it cost you?
Cost
I would say you get a research grant and you spend it based on what your supervisor tells you.
Yeah, exactly. I just asked my supervisor if I. Yeah, exactly. Thank you.
Just want to know how much they give you for stuff like this.
It all depends on what type of grant, where the PhD funding is from. It's just funding, really, and what's the scope of the project. Do they want to, I don't know, go down a transition method? Check how catalytically stable are they? Maybe some other projects. Then we define the scope and calculate the cost. The best probably PRs work for other students. Supervisor, principal investigator.
Yeah.
So can I ask a question? What is the whole aim of this? Are you trying to generate energy from this stuff?
Yes, we want to store energy into chemical bonds, like store sunlight or wind into chemical bonds like hydrogen.
So you want to create hydrogen?
Yeah.
And you want to use that to generate power. You want to burn the hydrogen to generate power, right?
Yeah, so we have fuel cell, which can convert hydrogen, the power in hydrogen to electricity. So it's like
fuel cells. That was something I was looking at a long time ago. Is this how it works? Is this what it is? As in what I'm saying, is this a basic?
It's half of the. So I'm looking at to store renewable energy into hydrogen, and the fuel cell guys, they will convert hydrogen into electricity for like daily use.
So after this hydrogen goes somewhere.
Yeah.
So you have a pump, right? And you pump it somewhere.
Well, now we're just generating very little amount of hydrogen, so it's fine. It just emit into the fume hood. Yeah.
An industrial scale.
Yeah, no, it's just lab scale. So
Okay, let's check.
yeah, if we generate really high amount of hydrogen, I'll be very happy.
Very simple.
Yeah, it's very little.
It's just like you can calculate how much you can make. There's obviously a clear finite limit of how much water is in the earth. Do we use all the water?
Yeah, we use water.
Do we use all of it? You can't use all the water on earth. It's just too much of it. Do you know what I mean? There's how much water is like, so what's factor, yeah, as in what is the water, but how much water? Yeah, let me sorry, yeah, sorry.
Yeah.
No, this is actually quite interesting.
Yeah.
You keep on and on about questions.
All right.
Yeah.
Sorry, I mean, I'll ask her later on. Actually, I actually read.
Yeah, so we use gold as a backing electrode and is most commonly used. However, recent publications showed gold is still problematic. And in this paper, they compared different backing electrodes like glassy carbon, boron-doped diamond, gold, as well as iridium oxide itself. Each of them has their own problem. And the conclusion is that nothing is more stable than iridium oxide, and the degradation in performance is very likely from the backing electrode rather than the degradation of iridium oxide itself. And the problem of gold is that it can readily dissolve and redeposit onto iridium oxide. So it will block the active sites of iridium oxide and cause degradation. What I found about gold is that the sputtered iridium can lose activity on gold after aging for a month. So that's the initial result and with very high activity. However, after a month, there's no activity, but the capacitance is still there. So it's really weird. But in the same batch of the sample, supported on FTO, they survived. So we need to understand what's going on here. But this result told us we need to replace gold. So where can we search for the alternatives of gold? And by the way, the OER conditions are really harsh. There are acidic electrolyte, oxidative potentials, and lots of oxygen. If you look at stainless steel, its corrosion resistance performance is from a passive layer of chromium oxide on top of iron. So that's why it's stainless steel. In terms of the requirements for OER supports, they also need to be corrosion resistant, plus conductive and abundant. Early transition metals are well known for their excellent stability and corrosion resistant behaviors, and they are quite abundant compared with these transition metals. And they are metals, so they should be very conductive. So in this project, we picked 6 early transition metals, 2 from each column, to study their stability and conductive under water oxidation conditions. So I've developed an interdigitated electrode to look at the conductivity change under water oxidation conditions in situ. So we have two working electrodes made of gold, and the samples were sputtered on top of this gold electrode to bridge these gaps. And these 2 working electrodes are operating simultaneously with a bias difference of 10 millivolts. Oops. Sorry. So the potentials applied here are to drive a catalytic process And the difference in potential is to measure the conductivity. Here's an example of 100 nanometers of titanium metal. So we can scan from 1.3 to 1.7 versus RHE and went back to 1.3. This symmetrical current means there's no Faraday reaction happening, and the difference of this current is proportional to the conductivity of the sample, according to Ohm's law. So we've tested all of these 6 metals, and some metals like tungsten, molybdenum, they seem to have formed the oxide layer and at 1.3 versus RHE already, and the hafnium is quite stable until 1.6, and this corrosion seems to be irreversible even when we scan back to 1.3. In terms of the long time stability, titanium, niobium, and tantalum remain conductive and stable even after 36 hours of polarization, while the oxide layer went deeper on hafnium and tungsten. And it's worth mentioning that the conductivity loss could be from the oxide or passivation layer on the metal, or the metal dissolution and the delamination of the thin films. So this interdigitated electrode were used to measure the in-plane conductivity, and it's safe to rule out molybdenum, tungsten, and hafnium. However, the through-plane conductivity is more relevant to the activity of iridium. So we've used ion redox couples. So we have peak separation here, which can be used to indicate the resistance of the thin film through plane. And so we tested these 3 metals, and only titanium managed to show the redox peaks. Iridium oxide was then drop cast onto titanium, tantalum, and niobium fumes. And after accelerated degradation test, only titanium was able to sustain the activity of iridium. And there's no activity at all when supported onto tantalum and niobium. This result confirmed the suitability of titanium to be used as the OER support. So at the moment, I'm focusing on titanium-based catalyst support, but it's still well known that titanium dioxide is still very insulative. So maybe making titanium oxynitride, titanium suboxide, or doping titanium oxide can improve the conductivity of titanium oxide.
Sorry, what does doping mean? I don't know.
Oh, doping is to make some foreign atoms into the. For example, if we dope titanium oxide, we can dope with other metals like niobium, tantalum.
Oh, mix it.
Yeah, it's like a mix, but it just won't change the crystal structure of the parent, the whole host. So let's take a step back to look at the degradation mechanism of supported iridium oxide. First, we can physically lose iridium by the catalyst detachment, and we can chemically lose iridium by iridium dissolution. Since oxygen evolution is a gas evolving reaction, so the bubbles can also block the active sites of iridium and cause the degradation in performance. The degradation can also be from the support, like the support. So the oxidation of the support can cause conductivity loss, and also the support can delaminate from its substrate.
What does OER stand for?
Oxygen evolution reaction.
What does GC stand for?
A glassy carbon. Yeah, sorry, I should have put something here.
No, honestly, it's just doing it.
Yeah, so in my project, I've used 3 types of mass spectrometers to look at gas phase, liquid phase, and solid phase of this reaction. So first is electrochemistry mass spectrometry. We can look at how much oxygen is being evolved during the reaction. And in terms of the liquid phase, like the metal dissolution, we can use inductively coupled plasma mass spectrometry we can quantify like how much metal dissolved. And the time of flight secondary ion mass spectrometry is to look at the solid phase. For example, the thickness of this oxide layer formed on the support. So this is the electrochemistry mass spectrometry data on iridium oxide supported onto different support. There's no doubt that the iridium oxide has the highest activity when supported onto bare glassy carbon and gold because they are the most conductive substrate. If we zoom in to look at this titanium-based support, we can see there is a really sharp onset of the oxygen signal, and then it decreased quite a lot and down to 0. Iridium supported on titanium niobium alloy, it has quite stable activity and higher activity compared with pure niobium and titanium. The electrolyte has been taken out at 5 minutes, 15 minutes, 30 minutes, and 90 minutes intervals during the reaction to look at the metal dissolution from both iridium and the supports. So major dissolution happened in first 5 minutes, which is in line with the literature, and it's called transient dissolution. It's because of the potential jump at the beginning of the experiment. So here showed a support-dependent dissolution behavior. You may have noticed that the highest dissolution always coupled with the highest activity. So how can we combine the stability and activity? Here comes the figure of merit called stability number. So that's it's defined as a ratio between the amount of oxygen evolved and the amount of iridium dissolved. So we calculated the stability number of supported iridium oxide and found titanium niobium alloy showed similar stability number with gold. So the last mass spectrometry is the time of flight secondary ion mass spectrometry, and it has a depth profiling function, so we can know the thickness of the oxide layer being formed. I'll skip how it works here, and so we look at this data. We did depth profiling before and after water oxygen evolution, and on gold there is no clear oxide layer formed after water oxidation, but this oxide layer has formed throughout the film on titanium nitride. That might have explained why there's no activity at all at the end of the reaction. in terms of titanium niobium alloy, we can see a distinctive metal oxide interface after water oxidation. And this oxide layer is just a few nanometers. So maybe it's still very conductive for the charge transport. In order to understand the oxidation mechanism of titanium niobium alloy, we first annealed the samples in air, and we could see niobium 3D orbital disappeared from XPS, which indicates that after annealing, the phase titanium niobium has been segregated with titanium dioxide formed on top of the thin film. So with regard to the electrochemical oxidation, maybe it could show similar behavior. So we polarized these films at 1.6 versus RHE, and the niobium ratio also slightly decreased after 4 hours polarization. That's also showed it segregated. So that could be a problem of titanium niobium alloys. So to conclude, it's really challenging to find stable and conductive support for iridium oxide water oxidation catalyst because nothing is more stable than iridium oxide itself. And the titanium-based materials seem to be the most promising candidate. But they're still suffering from oxidation, phase segregation, and conductivity loss under OER conditions. So finally, I'd like to thank my supervisors for their guidance throughout the project and my colleagues for the help. Thanks for listening. I'm here to take questions.
Yeah. Can I ask a few questions?
Yeah.
Questions now. Is that right?
The time has come.
Yeah, great.
How does the hydrogen fuel cell work exactly?
Hydrogen fuel cell.
Yeah, how does that work?
So I think that's the reverse process of electrolyzer. So it use hydrogen. It reduce or oxidize hydrogen by hydrogen oxidation process and make it into water. It's like a burning process, but it's just to use catalyst, no fire.
So so instead of catalysis,
Yeah,
it does analysis. It turns hydrogen to water.
yeah, and it can convert the energy stored in hydrogen into electricity.
So it works on the ionic principle. Is that how it works? It generates because water comes in different forms, right? And in different it can dissociate under different conditions. What I'm saying is, if you spent all that energy here to make hydrogen, why would you then want to turn it back into water for storage?
Yeah, because hydrogen
Well, it's-
has a very high energy density and it's light, so it's easy to transport. So that's why. And when we burn hydrogen, we don't get any CO2 emission.
So it is the best course of action to use hydrogen fuel cells as the energy after this process?
Yeah.
Or would it be better to just burn the hydrogen? What I'm saying is, which one generates more power? How much energy is generated from this? That's what I'm asking. Genuinely.
Yeah, so that's a question for the fuel cell guys. But
Okay.
yeah, but if you burn it, the efficiency of fuel cell should be also very high. But it just it converts into different types of energy. So if you burn hydrogen, it turns not to be heat. But if you use fuel cell, it will convert into electricity.
So which would be better option, in your opinion?
I think electricity, because we use electricity.
Oh, so you wouldn't burn the hydrogen.
No, and it's very dangerous to burn it. It can be explode.
Yeah, I know. Let me write that down. It's actually, I've got a few more questions. Okay, on average, how much energy do we gain? How much energy is generated? Like, how much energy? Like, what is the contribution globally on a large scale? Do you know what I mean?
Yeah, I see. Yeah, it's so what we are producing hydrogen, but only maybe 10% energy hydrogen is from electrolyzer, and basically they're from alkaline electrolyzer because it's well used in industry already. So it's from alkaline electrolyzer, but it requires very like high energy input, and it's so PEM electrolyzers is very small. It's just like that.
No, nice. Another question is, have you ever like, what is the whole like energy dynamic? Have you drafted like an energy profile diagram for this?
No, you mean, yeah, because I know hydrogen, they are mostly from I think from ammonia.
Hydrogen from ammonia.
I'm not sure, but
Doesn't that happen in
hash Haber-Bosch reaction?
Yeah, you can literally
Yeah, not many hydrogen from electrolyzers.
you use that in
Yeah,
get an old catalytic converter.
Yeah.
Slap ammonia in.
yeah.
We used to do that all the time. So that's what I'm saying is like, have you drafted an energy profile diagram for this? Because this could actually be very, very profitable. But how would you like tweak all this micro scale stuff in the bigger scale? That's what I'm asking.
Yeah, so the answer I'm trying to look at is not to make it a large scale. We want to decentralize it because because renewable energy are like very distributed. It's not centralized. So we want put maybe electrolyzer on your roof. Yeah, so it can.
That's actually a really good idea.
Yeah, so we have sunlight during the daytime, and we can store energy, like extra energy into electrolyzer, into hydrogen. And then in the midnight we can like have electricity.
Yeah, it's a really good idea, genuinely. What I'm saying is, how are you going to design it? Are you going to attach this apparatus to a photovoltaic panel? Is that how you're going to do it?
Yes. Yeah, so that's why the photovoltaics is not able to power alkaline electrolyzer because alkaline electrolyzer requires quite high, like very intense energy input. And the solar panels, maybe we need thousands of solar panels like tandem to power like a alkaline electrolyzer. If you look at the alkaline, they're really huge, like in the factory.
Yeah, massive.
Yeah, massive one. But the PEM electrolyzer is just like this big, and it can operate at very high current density.